Hey, today I'm just gonna do an integral transform um, video for just cause I want to share this and I want to know if it's actually legit. So, so we all know, or at least whoever's watching, I hope knows about this or what integral transforms are. I'll use this one. So I believe it's called Laplace's transform. So these can help solve differential equations that are like y prime prime plus 2y, but it doesn't really help when there are functional coefficients. So, and the reason is because it is there's no like neat or there's no neat like way to represent the functional multiple of a variable. So, however, I have been recently trying to come up with an integral or just a transform. It doesn't even have to be integral, where the transform of a derivative can be expressed as the transform of the function. So like j f prime. Now it doesn't even even though it isn't, even though like I'm just using this notation, but it doesn't necessarily have to be an integral transform. It just has to be some sort of transformation where it's going to be some known function, and then times f of t. So with Laplace's, it's fl prime is equal to s lf, but we want it to be inside it, or we want our transformation to be inside. So just to so this is kind of my thought process as well. So let's make it simple and let's just make it this. And then it can be plus whatever, but it can't be like plus f of, or let's worry about that later. We want this part. We at least want this part. So we don't, so let's not worry about that. So it's going to be j, actually, even if it's just a functional transform, but let's just make it easier on ourselves and see if we can do this. So the first thing that popped, or eventually I figured out is what happens if you did the derivative infinite amount of times. So like this. So limit as u approaches infinity is equal to, well, assuming is equal to plus 1. So, well, that is true because well, I'm not sure exactly if I'm pretty sure it's still true even if u is not an integer greater than, or I mean like we're talking about u is greater than 0 because I don't want to deal with the constant of integration stuff when you integrate. So u is greater than 0. So then assuming this limit exists, this part exists, then this will equal to this. Or yeah. So we have our first part. However, so our first part is going to be this. or it's gonna be similar to this. Our transform is gonna be similar to this. Now, generally, with general integral transforms, it's integration, some bounds, and I think it's like infinity or something. F of t k t v. So let's add, just cause, you know, I just did this. So k t. Now obviously so it's ktv. Now you could do ktuv. Actually, yeah, let's do kt. I think this is how I did it originally. So now it could just be a function of k and t and v, but let's just do yeah. So that, and then we want the outside to have t. We're gonna make this an integration problem. So tuv integration. Let's do we don't have to worry about the bounds just yet. We just have to have bounds dt. So a transform is going to be in the form of this. Okay, so our first step, so we don't really, so since, now this is linear. I'm pretty sure it's going to be linear since the derivatives is a linear operator, and so it's integration. So jf plus g equals jf plus jg, assuming both exist. So that's nice. So then now we want to make this. Let's get rid of this. So we want this. And actually, it can even be a constant since that's, you know, since it's linear. If it was, or actually even any, actually, let's just keep it like that. When I originally did it, it was a constant. I was trying to make it a constant times f of t, but let's just make it that. And there's a reason, actually, let's just do a constant. So it's a constant times f of t, or even, actually, no. Let's just do a constant, because I already know that's it can be a constant. Actually, no, you know what, sorry, let's just get one. Okay, so j, so let's do it. So j, so we don't have to worry about the j some function times f of t, we just care about the derivative. It's going to equal to f prime of t, which is equal to 2 plus f of t kt, which is the partial, this is partial derivative with respect to t. So just to clarify, so this is partial derivative of k with respect to t, and then you have to subtract it, f of t kt, which is going to be equal to, we can get rid of this, so minus f of t kt. Now this, if you know properties of integrals, is the same thing as this. So, so now we want this to kind of resemble f of t k of t, or sorry, f of t times k. So we're going to divide uv times k t uv. Let's move this over to this. So now this part, you might notice that oh, it's in the same form as this, except the u is off by 1. Now you could make k t u v equal to k t a transformation of this. But let's not do that, because that's just going, because I'm not sure if there's even a solution. But what we can do is this. So let's just get rid of the limits parts, because we're just going to, because we know u is approaching infinity. So, which means jf prime of t equals that. So then this is the same, well, you might notice, so we're going to essentially, this is the same thing as d over dt. However, yes, you know, because that's what we want, but we're actually going to put it outside, which is, and that's also equal to d over dt, this. And if you know I think it's called the UV transformation, I think you'll know where this is headed. So this is the same thing as this part is the same as minus integration a, or at least I think it would be equal to, yeah. So then, and then times this, and then the L T T U V. So then, now let's make it in the form similar to this. So we're going to over L T U V. Oh, I forgot the dt. And then L T U V. Okay. So now we have jf prime of t equals k of t minus integration minus integration okay, so now we want these. So in order for this to kind of have like a JFT, this can't have a t in it, which means this is going to be equals to G U V, and then this is equal to, well, we don't want a t in it, because then it's like, it's going, we want this. So so we want to see if we can make it, so this is going to equal 2, and then a way to get this out of here, well, since it can't contain a t, that means it's going to be a function of u and v as well. So then the result is L equals e to the power of g u v times t, and then times a multiple of u and v, but then that will get carried to, well, we don't really need that, let's just keep it m u v, and then k is going to equal to n, since it's the same problem, e to the power of h u v u v t. So then together, j f of t is going to be equal to n u v times m u v t. And then we can just bring this out, n u v, and then we can just simplify this as q u v. Actually, I like it when it's q u v. Okay, so we can do that. So then So if that's true, then kt, which is going to be this part, is just going to be, actually, let's just, kt over kt is just going to be hu of v. So then it's hu of v, and then the lt over l is just going to be gu of v. gu of v, actually. Which, oh wait, oh, this is supposed to be h, sorry. So now we want, which is just the same, so if we combine them, it's going to be the j of f times huv minus guv, and we want this to equal to 1. Oh, this is plus, because they both have minuses, sorry. So we want this to equal to 1, which means guv equals, huv equals 1 minus guv. So then, actually, I don't really want the thing in the inside, so we're just going to do the other way around. So guv equals 1 minus huv. So then huv negative this is minusing 1. So it would actually be is equal to -1, and then also makes sense because we kind of want it to approach 0 as, well, t is going to approach infinity. I mean, if it was positive t, then we just, well, actually, we want this, yeah, whatever. Yeah, let's just make it negative t because, you know, that's what, I don't know, I'm just inspired by Laplace. Or like, let's just do it negative t because just make it easier. I don't know, I'm just a classic positive to infinity rather than 0 to infinity rather than 0 to negative infinity. I don't know. It's let's just deal with it. It's not that big of a deal. So now, so then j f of t is equal to, now we're just going to, I'm just going to replace h with puv negative puv and then QUV. So I'm just going to erase all of this. So then it's going to be, so then it is plus jf prime, oh sorry, jf of t. Actually, no, let's just start from the beginning, and just, so we're replacing it with this. So this plus whatever, so that we want it to be similar to this. So let's try it. So this is going to be our transform. So jf prime of t is equal to limit as u f prime of t plus, and then we can just plus f of t p u v e power of p u v t, and then so subtract it. So then minus, I'm just gonna put the puv out of the outside. I mean, just imagine this replacing. Just imagine that we're not actually evaluating the u yet. We're just, it's just a shorthand of writing all of that. So then this is the same thing as d over dt which is just the same thing as times b to a minus and then minus negative p of u of v, which is going to be the plus pi of u of v. So then, and then the minus negative, so then it's just plus this. So which means f of t, which means j f prime of t equals that. Okay. Oh, I forgot the dt. Silly me. Okay. Now that we have that, we can focus on this. Well, actually, we want this to actually evaluate to something. So let's try j of 1 is equal to, well, f of t is 1. This is just going to be actually 1. It's just going to be e power p of u v t. And then times p of u v to the power of u. Then these cancel each other out. So then it's just going to be p u v to the power of u. We can move that times q u v e power negative t. Well, there's really only one bound, and I don't know, something tells me that I should probably have one of the bounds be equal to infinity. Because, I don't know, because if it was 1, there might be multiple functions, but even if it's not 1-to-1 like Laplace is, if it's, I mean, technically, what t plus 1, the transformation of d over dt, is the same thing as d over dt of t, but t does not equal to t plus 1, so it's like, yeah, so there could be multiple answers, but like, as long as it gives you 1, I'm fine. So then, and let's make this 0, it just cause, so then this is going to be negative e to the power of negative t. Let's just do a 0. Oh, so the limits are going to be 0, infinity. Well, technically, let's make this a bit more formal. Okay. 0 to a. So then j of 1. So this, I believe, evaluates to 0 minus negative 1, which is just 1. So it's this. Which means, so now we want this to equal to a function of v. So z of v, which means, obviously which means q u v is going to equal to, actually it could even be a function, it's just going to be, the q of v has to have a p u v to the power of negative u. And then times, yeah, let's just do h of v. So, but why would we multiply by h of v? Since all of them will be multiplied by h of v, so let's just get rid of that. We don't need to make this harder. We already need to. So then, times puv to the power of negative u. So then, puv to the power of negative u. So if qv is equal to that, so all of them, which means j of 1 is just going to equal to 1. Okay. Okay. Now that we have, so now we have to do the last part, p u v. Now, now we could, instead of trying to solve for like multiple different functions. Let's express f of t equal to the summation m equals 0 n cm e to the power of negative m of t, or m of t. I'm not. If I remember correct, I believe it was negative when I first did that. Yeah, because t goes to infinity, so we want it to be less. Okay, so f of t is equal to that limit, kind of like how like Maclaurin series, kind of how it's like, or even what are they called? I forget what it's called, but it's like the Maclaurin series is this Taylor series. So it's kind of like Taylor series, except you're using exponentials because of this. You'll see why. So then n approaches infinity. Yeah. So now, essentially, now let's just do one of the terms, because I just don't want to have to keep writing summations. So let's do f, or actually let's call this g of t. Actually, let's call this capital G, because so then g, actually no, let's just call it, yeah. So then now gm of t is just going to equal to one of the terms. So cm e power of negative m of t. Okay. So let's evaluate one of the terms. So then, so actually no, so it's in this. So it's going to be, f is going to be expressed as the sum of these, or g. Well, actually, so j, g, m, prime, or no, maybe, whatever. So j, g, m prime equals g, m of t plus j, g, m of t. So first we want to make the j known. So oh, actually we can just replace. So then so j, let's just replace e negative m, j negative m equals to negative m of t e to the power of, oh, sorry, this is supposed to be inside. Also, if this was, let's say, instead of plus j of t, it was plus a constant, well, each time you do the derivative, it multiplies it by c, and then each time, so if you wanted to do infinite amount of times, it will be, and if c is greater than 1, then it will be it will go up, and if it's less than 1, it will go to 0, so it kind of has, so we want it to be 1, because we want it to be still the same. Obviously, we're not going to be infinitely differentiating, but like, it'll just, I don't know, I'm just guessing. My intuition tells me it'll just make our life easier. So, okay, so let's first do j, actually let's do, yeah, so let's do jc of m e power negative t. So j, so then because it's a constant, this is a linear operator, j c m e to the power of negative m of t is going to be equal to, I'm just not going to bother with the limit part. Okay, so c, we can bring that out, and then e power negative m of t, which is just this. This, each time you take the derivative, it's just going to be this p u v minus m to the power of u, and then e power of negative m of t. We can bring all of this out. So then, so it's this over p of u, so then we can just do v power of u e power of negative m plus 1 of t. So our limit, so m is 0, and it goes up, up, up. So since this is always going to be greater than, less than 0, because, you know, it's going to, this part will, since a is infinity, towards infinity, is just going to be negative 1 over m plus 1 times negative infinity minus 1. So it's just going to be times negative 1. So it's just going to be this. So now we want, now if this was just a function of v, this, I believe, would just, it would approach 0, but we don't want that. So the first thing, or one of the first things that came out of me when I saw this was, hey, if this had a u in it, like, you know, because the limit 1 plus, or 1 plus z over, let's just call this w over z to the power of z equals e to the power of w. So if PUV had like a u in it, now I first tried u plus v, but you can just u plus v minus v. This will approach then times that times the power of negative v, which will just approach 1, because, you know, as you approach infinity, this approaches 0, so then it's just 1. And since v is kind of like a constant, or like it's a variable, but it's not, like we're not assuming it's like approaching infinity, so it's just going to approach 1. So then this will just be e to the power of m. So except, so let's actually, let's hold off on that. So we're assuming p of u is going to have a u in it, but let's just do this. P u v. So j. So assuming this is. So now we want this part. So this part. So we want to evaluate this. Oh, sorry. There's not supposed to be a dt there. Okay, and why did I put that? Okay, there we go. Okay, it's all fixed. So then it's, so we want to evaluate this. So then this, we can bring the cm out, kind of like with the above. Oh, it's kind of the same thing. You're evaluating the same expression. You're just not integrating the remaining part. Okay, so e power negative t would be, so it'd be p of u v minus m to the power of u e power negative m of t plus 1, and then, oh yeah, p of u to the power of negative u, so then it would be 1 over p u v. Okay. Oh. So now we want this to be defined, so we don't have to worry about this part. Obviously, yes, m will, or each m as it gets to infinity, but we're not actually evaluating at infinity. Like we're taking a limit. So this is going to be defined, which means in order for this to be defined, this has to be defined. So assuming this is defined as some value. So it's going to be Cm times value, which means we're going to multiply it by this. Now as t approaches, so m is greater than or equal to 0, which means this is always going to be negative. So then as t approach infinity, it'll approach 0, and since this is, which means it's defined as an expression of v, this will just approach to 0. So we don't have to worry about that. So now we have to value t at 0, in which case this will just be 1, and we have this, which means, minus Cm which means j, we can just do e power of, and it actually works and makes sense because what was it? So if you multiply all the things out, so it'd be 1 over m plus 1 minus 1, which is just m, over m plus 1, but and then so, oh, look at that, there's the m here. Well, we already know that JC in med is 1 over m plus 1, so then when you do it all of it, it's gonna be an identity. So yeah. So which means, but we don't really want to evaluate. We're just gonna keep this as gm of t. So we kind of know it's gonna be true, but we don't necessarily want to, equal to gm of t. So we just want this part. So then, which is going to be, so let's bring this down. It's going to equal to negative Cm power of u so gm of t. So now we have this. Oh, this is supposed to be prime. Sorry, forgot about that. So it's going to be equal to this. So there you have it. Although I haven't quite figured out, because if let's say PV has to have a value of v, else this will just be a constant. Well, obviously j of 1 is a constant, but like it'll have no v in it. It will never have any v. So this has to have a v. So let's just do an example. Is equal to, let's do PV equals u of v. uv, which is just going to be e to the power of negative m over v, or is it v over m? Nope, it's m over v. So negative Cm plus Jg of m of t. So, oh, look at that. This, see, the function is just gm 1. But we don't want that, because then when you sum them all up, it'll just be f, or it'll be g 1 over v. But we don't want this part to be a function of v of the unknown function, because we're trying to solve for we're trying to make it solvable. So if you could somehow make this, actually Cm is never going to be equal to 0. If you can make this part just a constant, yeah, if you can make this part a constant, but that's not really any possible, I think. So that, although except for 0. So if you can somehow make this equal to 0, then yeah. So which means, but that would mean PV does not equal to 0. So that means PV minus m approaches 0, but m will never, well, except for the beginning, will equal to 0. So no. So which means, oh wait. So actually, so this is the limit. So yeah, so you have to make this so you either have to make this, the limit of this, you approach either 0 or 1, or the inside. So this must either equal to 0 or it must approach to 1. Because else it's just going to be, actually no, it has to be, sorry. In order for this to approach, so this must be either less than or equal to 1, because if it's equal to 1, but that's not going to be the case other than m equals 0, so it must be less than 1, greater than negative 1. So if this, okay, so yeah, okay, so let's assume that. So that means this will approach 0. Except for when m equals 0, because then it's just negative cm, which will just be negative, oh wait, minus, I feel like, minus, I think that's right. Oh yeah, it is, yeah. So then this will just be negative cm, which is just negative f of 0, which, multiply this by negative f of 0, yeah, but like whatever. So let's just turn this on. So that means if this is true, that means, or less than or equal to 1. So we don't have, so if it's just 1, if m equals 0, it's just going to be negative c of m. So we don't have to worry about the 1. So assuming, actually, yeah, let's do this. Or even negative 1, actually. So then m over p of u of v is going to be greater than or equal to 0. P of u does not equal to 0. P of u must be greater than 0. Or less than, whatever. So m, actually no, p of u we do want to be greater than 0, because if we're doing it, p of u to the power of u, if it's negative, and if obviously u we're going to evaluate more likely on integers, but still, let's just make it greater than 0, or we can see what happens if we make it less than 0. So it's going to be this, less than or equal to 2, which means 0. So m does not equal to, so if m equals 0, it's true. So we don't have to, so excluding m is equal to 0, we're going to divide by m, greater than or equal to 1 over p u of v. So p of u, so assuming p of u v is greater than 0, that's going to be true. So then less than or equal to 2 over m. So then, so we want to find the smallest m not equal to 0, because as you increase m, actually no, we want to find the largest. Wait, 2 is m is equal to 1. Wait, if you increase m, oh, it gets smaller and smaller. So we want, I'm not exactly sure how to do that. So we want p of u of v to approach infinity. So the limit as u approaches, but we want to approach it at a certain rate such that this, I don't know how to make that true. So I think it's only 0. So I don't think it should be 1. Actually, so if you can make p of u faster than m, but you're valuing, so as u approaches infinity, so this means if it's equal to uv, but wouldn't that just be e per, no. So you want this to approach, or I don't know, you basically, you don't want this part to simplify into a function of v, because then, so yeah, so you want this to be like a constant or so, yeah. So if you could somehow make it approach 0, so I would say 0 is the optimal. So if you could somehow make this approach 0, which means or actually one, I think, because that would mean P of U approaches M, but we want to approach infinity. So that means P of U, the limit as U approaches infinity. Actually, you should know. So it's this. So the limit as U approach. Wait. So we want this.